How is it breaking it up?
Breaking bonds.
You're on the right track. It's not going to break the carbons apart.
Breaking IMFs.
IMFs. That amount of energy is able to overcome the intermolecular forces that are holding that sugar together. So are the carbons and the hydrogens and the oxygens separating from each other in the sugars?
No.
No, but the individual molecules are separating from each other, and then they're going to be evenly distributed. So now, based on entropy, why is it more likely to find those particles all dissolved in solution than to keep the solute and the solvent separate?
System has
Many more possibilities for locations for those particles in a solution. So solutions tend to be thermodynamically favorable. The formation of solutions tends to be thermodynamically favorable because now there's more possible arrangements for all of those particles than if you were to keep them separate.
Oh, I didn't know.
So remember when you put them in the video?
Yeah.
Carbon dioxide. I even put them. One original 270. So yeah, so these copies are just that.
Oh, I didn't know where the buffer solutions were.
Oh.
I didn't know if that would be I don't know where those guys are.
The models.
Not the models,
Oh.
the
Oh, yeah.
spectrometer.
So the tubes go in that, the small tubes in the boxes go in that box that's back there.
Mm.
And the other ones go up. And then that green box, I think it has like weird connectors.
Yeah.
That goes with lab pro stuff.
Right.
And then I'll put those green ones. But if the spectrum tubes, the actual glass tubes go in the box, and one of those spectrum tubes goes in that box. Use that box, it's fine. Great. And that's it.
And what about the buffers?
So they go on the shelf. I'll just put them on the shelf.
Okay.
They go on, I know, they don't have a sort of specific location. There's a couple other buffers there, but I know where to find them. I don't know if you've
Yeah. Gotcha.
Okay, so what does the second law say again?
Entropy is always increasing.
The universe is always increasing. Does that mean the entropy of the system always has to be positive?
No.
Of the surroundings?
No.
Doesn't have to be. So now we have to figure out how do we find the entropy of the system, how do we find it of the surroundings, and then how do we find it of the universe? Well, how do we find it of the universe? Just add them together. Find it for the universe, you just add the entropy of the system plus the entropy of the surroundings, which means we need to find a way to find both of these. What we've been talking about so far is how to find the entropy of a system. How do you find the entropy of a system? You're looking at its what?
Options.
Yes, and even easier, how much what there is in it. Possibly, but disorder, how much disorder there is. So if we're looking at the changes, it's going from like a solid to a liquid, the disorder is increasing. For surroundings, it's a little bit different, and that's where you're going to be tricked if you mess up all of your signs. But if this is positive, it means that the overall process is what? Spontaneous. What's the other term for spontaneous? Thermodynamically favorable. If this is negative, what does that mean? Spontaneous in the other direction. Spontaneous in the other direction.
Does that mean it won't do anything? Like it won't react?
Like, you can write it on paper, like this reaction is going to occur, but if it's not under the right conditions of temperature and pressure, then it would say, then like, instead of this thing turning into this one will turn into this under those conditions. So yeah, the reactants won't react to form products, but the products will potentially react to form reactants.
But if there's like no products there, it just stays the reactant.
Yep. Okay, so then how do we find what both of them are? And this is the part where it's going to get a little bit weird, so I'm going to make sure you're ready. Okay, so you've got your system, which is usually what our focus is. So something's going on here, then you have your surroundings around it. We're going to talk about the surroundings first, because kind of the system is like, if you're going from a solid to a liquid, the entropy of the system is what? Increasing. So delta S, the system would then be what? Positive. If you're going from a gas to a solid, then the entropy of the system is going to be negative. Okay, now let's think about the surroundings. So, if the reaction that occurs is exothermic, what does that mean it's doing? Releasing heat where?
So the surrounding.
And then what is it causing the surroundings to do? The particles in the surroundings.
Move
To
faster.
move faster, and then what? What happens to the entropy then of the surroundings? It's increasing the entropy of the surroundings. So exothermic processes increase the entropy of the surroundings. So the delta S of the surroundings is determined by delta H. But if it's exothermic, delta H is what? Negative, and delta S of the surroundings is positive. They're always going to be opposite. That's fun. So for exothermic processes, delta S of the surroundings is positive. But delta H is what? Negative. Don't be tricked by that. And don't also be tricked by this. To find delta S of the system, it's not opposite of this. They're not opposite of each other. Delta S of the system and delta S of the surroundings are not opposite of each other. They can both be positive, they can both be negative, or they can have opposite signs. Because delta S of the surroundings is only determined by whether or not the reaction is exothermic or endothermic. The sign of delta S of the system is determined by what? Yeah, what is happening? Is it becoming more disordered or less disordered? So I just put the opposite, right? If it's an endothermic process, delta S of the surroundings is then gonna be negative. And again, good, it's difficult there to keep all the signs apart. Okay, so the other last thing, only last thing I have. I would hit them for myself, cause I don't know. So that should go with G, so if you find G, that should go with G. I don't know how that got separated. I'm trying to read that. 3 or 5, so I don't know that you have time to look at any of it. I could probably find it.
For the surroundings, the delta S and the delta H will always be opposite.
Yeah, because if it's exothermic, delta H is negative, but delta S, the surroundings, is positive. But that has nothing to do with delta S of the system.
Okay.
Okay. So let's look at this process specifically. So this one. So if I'm going from a liquid to a gas, the particles are becoming what as far as delta S of the system? They're becoming more disordered. So delta S of the system is what? Increasing. So what's the sign? Positive. So delta S of the surroundings is determined by what? Delta H. So then let's look at it. To turn a liquid into a gas, what do I have to do? I have to put energy in it here. So if I'm putting energy in, delta H is positive, but delta S of the surroundings is negative. So will this process be spontaneous? What does it depend on? Temperature. Depends on temperature. So at certain temperatures, this will be a spontaneous process. At other temperatures, this will be a spontaneous process. So you have to know the temperature to be able to calculate that.
So delta H is positive, you want, for it to go that way, you need a low temperature, so.
Delta H is positive, you need a high temperature. Because if delta H is positive, that means it needs to take an energy. So if it's in an environment where there's a lot of heat energy available, it takes it in, and then it becomes spontaneous. Lots of signs, and it's a little confusing. So you just always have to say disorder. Can I go on to the next one? Yeah? Okay, so I kind of have already said this, so it's a little bit repetitive, but just to remind you, say it. When the entropy of the system increases, the delta S of the system is positive. So if disorder of the system is increasing, delta S of the system is increasing. So how do you find delta S of the system? You're only looking at the what? Yeah, the amount of disorder, like what's happening. Is the state changing and what? How do you figure out the delta S of the surroundings? Delta H, is heat going in or out of the reaction. So now let's look at this one. It's now kind of a reverse process. Now if I'm turning a gas into a liquid, how about delta S of the system? A gas going into a liquid, what's happening to disorder? Decreasing, so delta S of the system? Negative. So for this process, turn a gas into a liquid, endo or exothermic? Exothermic, so heat is coming out, so delta S of the surroundings? Positive. So is this process spontaneous? At certain temperatures it will be. Okay, one other thing that sometimes you'll see, so just so you know this, if it doesn't say system or surroundings or universe, and it just says delta S, what do you think it's talking about? System, because what is always our focus? System. So sometimes it will just say delta S, and just know if it doesn't tell you surroundings or universe, then it means system. If it ever wants to know the delta S of the system, the delta S universe, it has to be specified. Okay, so then what do we do with temperature? So then the last bit I want to talk about is how do we deal with temperature? Tomorrow we'll calculate stuff for temperature, but not today.
So if the system, okay, so if the system surroundings, if one is positive, one is negative, temperature depends on spontaneity.
Temperature determines spontaneity, yes. But if they're both, what if they're both positive?
It's spontaneity.
What if they're both negative?
It's negative.
There you go. You just figured it out, that's like what I'm getting. You just summed it all. You didn't have to listen the rest of the time.
Didn't even write it down.
Wait, you gotta write it down, it was a great thought you had. Can I go on?
You read the PowerPoint.
Oh, wait. That's good.
We looked at the PowerPoint for years.
I tried.
You should all do
I
that.
actually tried, but no, it doesn't actually. Because I heard
But
that
like all the
we were
past,
going,
Oh, what?
all the past units, I told myself I was gonna print out the PowerPoints and take notes on them, but I haven't yet. Maybe
Did you do on this one?
no.
There's only 2 left, this is it, is this one or the next one?
Pull it up
Well,
on
then
your
I guess
phone.
Wait, no, but I like to take, I wanna take notes like.
Well, really, it just, 2 more PowerPoints for the year.
Well, 2 more chapters, 16, 17, for the year. So 2 more chapter power,
Maybe
yeah.
I'll just,
How long do we have until like after 17? Between that and
3 weeks.
I'm actually not allowed.
So we'll finish 16, finish 17, there's probably a week before spring break. We'll do a little organic, a little nuclear, a little stuff for like a week, and then it'll be spring break. When you come back from spring break, there's only 3 weeks exactly till your AP exam, which, I don't know if you looked at the date,
I just feel like how much other people back. The month.
it's March 2nd.
2 months from today, you'll be doing what? 2 months from today, at this very time, you'll already be done with the AP chemistry test.
The exam?
do you know what that means? Oh, 9 days.
I was like, if you're counting down your birthday in months, 9 months is my birthday. 9 days your birthday, that's a little bit different. That's a little bit different. All right, so temperature and spontaneity, last thing, ready? All right, so I've already said this, but this is super important, which is why I keep saying it. Entropy changes in the surroundings are only determined by heat flow into or out of the surroundings. Which ones do you think are more favorable? Whether heat is flowing into the surroundings or out of the surroundings. Exo, which would be exothermic reactions will release heat where? Into the surroundings. So exothermic reactions are often favored. So if it's ever asked which of these is favored, you'd say, oh, exothermic reactions are favored, but does that mean that they are always going to be spontaneous? No. Because you also have to know how much disorder is increasing or decreasing. But usually exothermic processes are favorable.
The more heat that goes in, the more disorder.
Usually, but that's not always true.
Okay.
So the size of delta S of surroundings depends on temperature. And so you can calculate, be careful with this. This only is used to calculate delta S of the surroundings. Delta S of the surroundings is negative delta H over T. Why is there a negative? Because what did we say about the sign of delta S of the surroundings and the sign of delta H? They're always going to be opposite each other. Yep. You can't calculate delta S of the system or of the universe using this. It's only of the surroundings. That's it. And this is not on your blue sheet, so this is one that you need to know. If you find the delta S of the surroundings, can you tell me whether this process is spontaneous or not?
Well, if you know the system.
If you know the system, but by itself you can't, right? Okay.
So they're in, you're getting separated.
Let's see. This is